Hi, folks, and welcome to another video where I'm hoping to illustrate some facts about perhaps a couple of homework problems that you've already had. Have you encountered a homework problem that uses the word nozzle? Similarly, at least one section has got a homework problem that mentions the piece of equipment called a diffuser. And so what I want to do in this video is to illustrate what are those two, how are they similar, and how are they different. So here goes. Nozzles versus diffusers. And so here's what we want to accomplish is really define and what is a nozzle? What does it look like? What is a diffuser? What does it look like? And how are these different and how are they similar? We'll look at a classic application of the continuity equation that really simplifies down for these two types of equipment. We'll look at some basic examples, one dealing with incompressible fluids. That's where density is constant. Compressible fluids, things like ideal gases, steam, refrigerant. And then last section having to do with nozzles is achieving supersonic flow. And we'll try to give a couple examples of that. And then application, talking the application of the first law, which can be really very powerful and I think pretty easy to understand for these types of equipment. Well, this is a nozzle. It's something easy to see, easy to visualize. It might be made out of brass. It might be made out of aluminum or stainless steel. It could be made out of a carbon composite material. But basically, all you need to know is it's sort of like a slab of material, hollow on the inside. Flow is going in with a low velocity. You see this converging area, and then the flow goes out with a higher velocity. That's what a nozzle is all about. Now, this is a diffuser, so interestingly, you'll see that the piece of equipment did not change. All I showed on my sketch was you've got flow going in the smaller area and flow leaving the larger area, flow going in with a high velocity, flow leaves with a lower velocity. Okay. Oh, and what these two have, what do they have in common? Both would be open systems. I see mass flow in and out, steady state, steady flow. The mass inside this piece of equipment is neither getting fatter or skinnier. It's a steady situation, and the state at the inlet is the same at all time, and the state at the outlet is the same at all time. Steady state, steady flow, one inlet and one outlet. So let's compare. Nozzle, flow goes in with a lower velocity, leaves with a higher velocity. Diffuser goes in with a pretty high velocity, leaves with a lower velocity. How are these similar? Well, both are open systems, steady state, steady flow, one inlet, one outlet. Let's study work or power. Do you see a rotating shaft leaving these control volumes? I don't see a rotating shaft. Do you see these basically pieces of metal? Are they lifting a weight? Are they lifting a weight as part of the process? No, they're not lifting a weight. And so therefore, the conclusion is for this flow situation where there's m dot operating at a rate, there's zero output power. W dot out is zero. Okay. So the process objective, similarly, both of these, is to change the kinetic energy of the flow. For the nozzle, our objective is to increase the kinetic energy. For our diffuser, our objective is to lower the kinetic energy. Okay. And so basically, how are they different? The process objectives are exactly the opposite of each other. Oh, time to go live to show you some physical examples. All right. Here's a great example of a nozzle. This is a plain old garden hose nozzle, right? Well, let's look at the inlet diameter. Okay. Okay, I think you can see that, I think, on your screen, inlet diameter. probably about 3/8 of an inch. Exit diameter. Very hard to see because of that plug, but there's a very small annular opening. And if you could get a hold of this garden hose nozzle and do the math, you'd see that the outlet area is a much smaller outlet area than the inlet. And so I hope that you can see how this garden hose nozzle could be modeled easily with that sketch that I just showed you. Okay. Another example. I just made out of parts from Lowe's. This is a homebrew nozzle. Okay. And just out of PVC parts. And so let's, and here, this would be the inlet. This would be the outlet. And so let's see what we can see in here. So we're going to look at this. If I get this set just right, you can see both the inlet area and the outlet area. If I can hold this still. So you see the inlet area is closest to you, big, and the outlet area, much, much smaller. So this is just a good example. And do you see how this would be a steady state, steady flow control volume? One inlet and one outlet. This equipment's neither getting fatter or skinnier. It's just sitting there with some flow going in and exactly the same flow going out. Homebrew nozzle. Next thing to show you is a real nozzle. This is a brass nozzle from a Sidewinder air-to-air missile. Okay. Now you are going to see that you're going to say, wait a minute. This is both. Here's the inlet. Okay. Here's the outlet. Now on this show and tell, you'll see that, well, this is called a rupture disc. And so for this missile rocket to operate, there's going to be a fuel and oxidant here. And once that's lit off, the pressure will increase so high that this rupture disc will rupture. And then you're going to have flow into this nozzle and, of course, out of this nozzle. Steady state, steady flow. Now you're observing, wait a minute, I see that I've got a converging section and a diverging section. Well, there's going to be I've got a few more details about that a little later, but it turns out that now let's look at inlet area. Inlet area pretty big, right? Inlet area pretty big, and outlet area is somewhat smaller. And so just to give you a little heads up of what's coming on, the flow out of this is going to be supersonic, and there's some design details associated with designing this rocket nozzle appropriately, but do see that the inlet is big, outlet not quite so big. Supersonic rocket nozzle. Another example of a rocket nozzle, okay, made out of a carbon composite, okay. This is inlet, I think inlet going in, outlet coming out, okay. And then this is a cross-sectional view. So someone's cut this thing right down the middle. And so you can see what this looks like, a converging section to a throat, to the lowest area. And then slowly the area slowly increases back, but still not to the point of the area of the inlet. Okay, so you see that this is a supersonic rocket nozzle, and this is for a Hellfire missile. And a few more details of that later on in this presentation. But this is also a nozzle, rocket nozzle for supersonic flow. Now back to our presentation. All right. Let's look at the continuity equation and how it applies to both nozzles and diffusers. Basically, application of continuity equation. I have shown a nozzle, but if you recognize you can just sort of flip things around, these fundamentals are going to apply exactly the same to the diffuser. Open system, steady state, steady flow. One inlet and one outlet. Since it's steady state, steady flow, m dot equals m dot 1 equals m dot 2. Remember the jingle. M dot is rho 1A 1V1. Exactly equals rho 2 A2 V2. Great application of this continuity equation. Also, in your book, remember, m dot equals A1V1, the volumetric flow rate, divided by the specific volume at 1, equals exactly the volumetric flow rate A2V2 divided by the specific volume at 2. So easy to remember. It's my hope that you could commit this to your memory as it applies to a nozzle or a diffuser. Now, what I want to do is look at I'd say the easiest type of nozzle working with incompressible fluids. Okay. The most commonly occurring incompressible fluid we have in engineering is water, because water is so commonly occurring. So to remind you, what's incompressible fluid? That's one in which rho is constant. So continuity equation, ρ1 A1 V1 equals ρ2 A2 V2. Both of those densities are numerically the same. Okay, so let's write down what we have. Basic for incompressible fluids. So now we've got open system, steady state, steady flow, one inlet, one outlet. Okay, the sketch. Okay, incompressible fluids. Well, I realize now that m dot, it's the same at the inlet and the outlet. If rho is constant, I'll divide by ρ1 equals ρ2 and get A1 V1 equals A2 V2. The volumetric flow rate inlet equals the volumetric flow outlet for incompressible substances. So it's kind of cool. We can quickly solve for V2 as long as we have V1. So V2 is simply V1 times the area ratio, A1 over A2. Really very easy for incompressible fluids. Now, I suggest you don't memorize this business. This would be like a formula. You don't need to memorize that. But by golly, I sure hope you have got this in your memory and then can derive the special relationship for nozzles or diffusers with constant density, incompressible fluids. Classic example of a nozzle is fire hose nozzles. Here's a modern fire hose nozzle that these guys are holding. Notice here, because of the large flow rate going through this nozzle into and out of the nozzle, you will learn in fluid mechanics class that it takes a lot of force to hold that nozzle still. That nozzle is pushing back on these two firefighters. Okay, you're going to be able to compute that in your next fluid mechanics class. And then here's some pictures of old school fire hoses that were very long brass nozzles. They were beautiful, but you really don't see these used much anymore. More compact fire hose nozzles nowadays. Here's my homebrew nozzle. And so, for example, let's say we have a homework problem and somebody says, I've just homebrewed this nozzle, okay? And I'm able to deliver 20 GPM, 20 gallons per minute of water to my homebrew nozzle. What's going to be the inlet and exit velocity of my nozzle? Very straightforward homework or quiz or test questions. How will we approach this? Okay. Well, of course, we'll know it's steady state, steady flow, open system, constant density, because we're dealing with water, 20 gallons per minute of water. Okay. We'll determine the volumetric flow rate. We'll have to convert 20 gallons per minute to cubic feet per second. We're going to have to do some physical measurements, the inlet and outlet areas, determine that. And then finally, very straightforward, to use the definition of volumetric flow rate to determine the inlet and outlet velocities. Okay. All right, well, let's go do our homework. So I did some offline. I went offline and measured the inlet and outlet diameter of our homebrew nozzle. Inlet diameter is 3/4 of an inch, nearly exactly. And outlet diameter is 3/8 of an inch. Okay, got it. Now write that down on paper. All right, so here's the solution. I'm going to start with 20 gallons per minute volumetric flow. I'm going to go to the book and write down this conversion factor, 0.13368 cubic feet equals 1 gallon. So I'll do that math to get a volumetric flow rate of 2.674 cubic feet per minute. Now, to get my unit straight, I need cubic feet per second. So I'll divide that by 60 seconds in a minute, of course, to get volumetric flow rate 0.04456 cubic feet per second. All right. Now let's see. I need some areas, inlet outlet areas. Very straightforward to do the math and the units conversion to get the inlet area pi over 4d squared to be 0.003068 inlet area square feet. So the inlet velocity, therefore, is the volumetric flow rate divided by the area, or going into our homebrew nozzle, 14.5 feet per second. Coming out, outlet diameter is known, so the outlet area, 0.000767. I've got to move my Zoom menu so I can read my slide. Okay. Outlet area, 0.000767 square feet. Using volumetric flow rate definition, the outlet velocity is 58.1 feet per second. And if we study on that ratio, you'll see that the outlet velocity is 4 times the inlet velocity for only half the diameter. So that's a really cool observation for our homebrew nozzle or any nozzle. So you really get a lot of bang for the buck by decreasing the area from the inlet to the outlet. Okay, let's move on to working with compressible fluids. That's one in which the density is not constant. Let's say one in which you might be heating or cooling air. That density is not constant with the ideal gas air if you're heating or cooling it. Okay. This little picture I've been showing is a commercially available piece of equipment. You can order up a nozzle and treat it, and you can use it either as a nozzle or a diffuser. It's just a matter of which way you install it. You can order it from a supplier. Another example of a nozzle or diffuser would be in the air conditioning, HVAC, heating, ventilating, and air conditioning area, where we have, this is just plain old aluminum or steel, and it's formed into a square to round adapter to go from or to a square duct, from or to a round duct. But clearly, by observation, for this example, A2 is less than A1. You're necking it down. This would be the functionality of a nozzle. Okay, kinetic energy is increasing for this flow situation. If we reverse the flow to this easily available piece of ductwork, we're going in at a certain kinetic energy, coming out at a lower kinetic energy. This is the diffuser functionality in which A2 is greater than A1. Kinetic energy is decreasing. So I hope you get the feel for what a nozzle or diffuser equipment is all about. Now you could go, it's easy to order. This is just sheet metal. This is just formed sheet metal that you can buy. Another example is a steam flow meter. So in power plant situations, in industrial situations where we must measure m dot, we have to figure out m dot of the steam going here and there. A steam flow meter is a classic example of a converging, diverging section in which the inlet and outlet area basically is the same. But what's going on here is we're converging the flow like a nozzle. We're making some pressure measurements. And it turns out you will learn in your fluid mechanics class how to figure out the flow rate of steam from this change in pressure measurement. And then once we're done with that, we go to a diffuser diverging section to let the kinetic energy reduce right back down to where it was at the inlet. Okay, so classic example of a nozzle and diffuser section that's enabling you to make a pressure drop measurement. The next section, I just want to make some remarks and maybe get you interested in a senior level thermodynamics / fluids class called compressible fluid flow or fluid dynamics. And so if you have interest in rocket nozzles, you want to think about taking that class. Achieving supersonic flow, in other words, flows where the kinetic energy is very high, very, very high kinetic energy. Here's an example, okay? And so here are some photos of that Sidewinder rocket nozzle that I showed you. Okay, it had a brass. Okay, this is just static pictures of that very rocket nozzle. Here's the exit area to give you a big picture of how does this piece of equipment fit with the objective. Well, this is the exit area of the rocket nozzle. So the fuel and oxidant will be contained within the Sidewinder missile. And of course, there's the missile being launched from the bottom of the wing of a plane, air-to-air missile. Okay, a few more details about this Hellfire air-to-ground missile rocket nozzle. I believe that the original purpose of this was to be launched from a helicopter for anti-tank weapons, but now the technology has been expanded to base any air-to-ground application. Okay, and so here's the Hellfire missile being launched, I think probably from the wing of a plane, I believe, maybe a helicopter, not sure. But then here's a nice image of the overall Hellfire missile. It's kind of interesting here that you can see that this spherical vessel would contain the oxidant needed to combine with the solid rocket fuel you see in here. And when that's lit off, then you're going to get this large pressure supply. You can see the converging section of the nozzle, and then you're going to get a supersonic flow coming out the back end of this rocket nozzle. If you're interested in taking this course called Fluid Dynamics or Compressible Fluid Flow, you're going to understand and learn the details of the careful converging, diverging nozzle design needed to achieve supersonic flow. And so this is simply a quick look where green represents low kinetic energy, red represents extremely high kinetic energy. It does turn out that at the throat of this nozzle, this is called the throat, the minimum area, that's where we achieve sonic flow velocity, the Mach number of 1. And then with proper design, as the flow continues to expand, we get supersonic flow in the diverging section of this nozzle. So this is an example of what you can learn in a next level thermodynamics, fluid mechanics course called Fluid Dynamics. So the objective, we start with low kinetic energy. Let's say where we light off the fuel and oxidant, low kinetic energy, but we want to transform that into very high kinetic energy to provide thrust for the rocket. Now let's finish up talking about the first law of thermodynamics for a nozzle or a diffuser. It turns out that I want you to see how really easy this becomes. All right, I'm going to state, here's the first law of thermodynamics for any open system, steady state, steady flow, one inlet and one outlet. This should look very familiar to you. It is my hope that you have committed this to memory. Q dot in minus W dot out equals M dot times a bunch of bracket terms, M dot times a bunch of stuff. And that bunch of stuff is the quantity enthalpy change plus kinetic energy change plus potential energy change. If you haven't got it committed to memory, at least you can kind of remember these words. Now let's simplify. Let's simplify for our, and I've shown a nozzle, but this will apply just as much to a diffuser. Okay. Let's knock out terms that we can. Potential energy change. Well, let's study the sketch. The potential energy from 1 to 2, no change in potential energy. I'm holding this control volume in my hand. You can see that there's no change in potential energy to speak of, right? No change. So I've struck that out. I hope that I've convinced you that there's no shaft coming out of this control volume. And this, when operating with flow, this control volume is not lifting a weight. Now, the kinetic energy is transformed into thrust to lift or propel a rocket, but the control volume is not doing any work. The control volume is not doing any work. So W dot, the output power, is 0. Look, for control volumes, look for a rotating shaft. For open systems, look for a rotating shaft. That's the way to identify output power. Look for a rotating shaft. So I've struck out W dot out. Now, when this control volume is fully insulated, if we could wrap this with insulation, and in many cases it is, that Hellfire missile was wrapped with insulation. Okay. When it's fully adiabatic, when you're fully wrapped with insulation and you have an adiabatic process, heat transfer is zero. So we will strike this out whenever the open system is fully insulated. And so can you see and then once you do that, you can divide by m dot. Okay. Once you divide by m dot, do you see that there is an interchange? Now look at what you have left. 0 equals enthalpy change plus kinetic energy change. So you have a balance. Okay, that's the key observation. When the nozzle or diffuser is fully insulated, adiabatic, there is an exact balance between enthalpy change and kinetic energy change. That's a real neat thing to observe for this type of equipment. Okay, so what did we cover? I hope now you have a much better feel for what's a nozzle and what's a diffuser and how are they different? How are they the same? We looked at, we saw both are steady state, steady flow, one inlet, one outlet. The mass flow rates are exactly equal, and rho 1 A1 velocity 1 equals rho 2 A2 velocity 2. We looked at the first law for steady state, steady flow, one inlet, one outlet, and we saw that in all cases, the enthalpy change is at least proportional to the kinetic energy change. When it's adiabatic, when the process is fully insulated, enthalpy change exactly equals kinetic energy change. When there is heat transfer involved, let's say when there's heat rejected, and it would make sense, there might be some heat rejected from this brass to the surroundings. When heat transfer is involved, these two are simply proportional to one another, but there is a linear relationship between them. Okay, that's what I've got, and I hope that helps you to better understand homework problems that are related to nozzles and diffusers.